Hello friends, in this video now I'm going to take shuttles. I told you one basic point that NADH, it cannot cross inner mitochondrial membrane. Even oxaloacetate cannot cross inner mitochondrial membrane. But pyruvate, malate and aspartate, these molecules can cross inner mitochondrial membrane, right? Now NADH is required for ETC. ETC occurs in mitochondria, but how NADH will go from cytoplasm to mitochondria? Because we require NADH as a starting material for ETC, so as such NADH cannot cross the membrane. So we require shuttles here for the transport of NADH from cytoplasm to mitochondria, right? So we have two shuttles for the transport of NADH from cytoplasm to mitochondria. One is malate shuttle, other is glycerol phosphate shuttle. In malate shuttle, what will happen? Let's say this is inner mitochondrial membrane, left side is cytoplasm, right side is mitochondria. In malate shuttle, what happens? That NADH is taken from cytoplasm and NADH is delivered in mitochondria, right? But what happens in glycerol phosphate shuttle? That, let's say again, this is inner mitochondrial membrane, left is cytoplasm, right is mitochondria. Now in glycerol phosphate shuttle, NADH is taken from cytoplasm, but what is delivered in mitochondria is FADH2 is delivered in mitochondria, right? So solve this question. Shuttle is required for. Options are glycolysis, link reaction enzyme, pyruvate dehydrogenase, TCA or all. What is the answer? You know, shuttle is required for transport of NADH from cytoplasm to mitochondria so that NADH can take part in ETC. But now see the options. Glycolysis occurs in cytoplasm, link reaction occurs in mitochondria, TCA is occurring in mitochondria. So these two pathways are already occurring in mitochondria. They are already producing their NADH in mitochondria, which can directly go into ETC. There is no requirement of shuttle, but shuttle is required for that pathway which is occurring in cytoplasm, because shuttle will take NADH from cytoplasm to mitochondria, right? Now, whenever we do energetics calculations, then we consider malate shuttle by default. We take malate shuttle. But a question was asked that if aerobic glycolysis will use glycerol phosphate shuttle, then how many ATPs will be obtained? You know that in aerobic glycolysis, normally we get 7 ATPs when we consider malate shuttle. But now you have to consider glycerol phosphate shuttle and do the calculation. See how we will do. You know, in cytoplasm, the energetics of glycolysis is this, that glucose forms 2 pyruvate, and in these 10 steps, we have -2 because 2 ATPs used at hexokinase and phosphofructokinase. We have +4 ATPs because 2 substrate level phosphorylation steps are there which are producing 4 ATPs. And at glyceraldehyde 3-phosphate dehydrogenase step, we have 2 NADH produced. And these 2 NADH are produced in cytoplasm. But these NADH have to give ATP by entering into ETC. So this is cytoplasm, this is inner mitochondrial membrane, and this is mitochondria. So this NADH has to go into mitochondria. And the question is saying it will go with glycerol phosphate shuttle, glycerol 3-phosphate shuttle. You know that by glycerol 3-phosphate shuttle, we will be obtaining FADH2 in mitochondria. This was 2 NADH, so this will be 2 FADH2. Now 2 FADH2 will give 3 ATPs, right? So you have to count this total, -2 + 4 and 3 ATPs, and your answer will be 5 ATPs. Now instead of 7 ATPs which we normally get via malate shuttle in glycolysis, now in glycolysis glycerol phosphate shuttle aerobic glycolysis will give you 5 ATPs, right? So 5 ATPs is the answer to this question. Now let's see the detail of these shuttles. What are all the enzymes involved here, right? The first one is malate shuttle. In malate shuttle, the name of enzyme is malate dehydrogenase, right? And in glycerol phosphate shuttle, the name of enzyme is glycerol 3-phosphate dehydrogenase. Now malate shuttle is important in liver and heart. Glycerol phosphate shuttle is important in skeletal muscle and brain. Now let's see the malate shuttle detail first. See, this is cytoplasm, this is inner mitochondrial membrane, this is mitochondrial matrix, right? Now in cytoplasm, let's start from oxaloacetate. Oxaloacetate. Now every time in shuttle, we have to complete the cycle, right? We are going to start from oxaloacetate, we'll be finishing also at oxaloacetate, right? So let's see. Oxaloacetate is converted to malate. Do you remember last step of TCA cycle was malate to oxaloacetate. Now it is opposite, oxaloacetate to malate. In TCA cycle last step, NADH was produced. Now NADH will be used. So NADH used, name of enzyme is cytoplasmic malate dehydrogenase, MDH, cytoplasmic malate dehydrogenase, forming malate. I told you malate can cross in a mitochondrial membrane, reaches mitochondria. Here malate will be converted to oxaloacetate, and this is the same step of TCA cycle where NADH is produced. This NADH can go into ETC to give 2.5 ATPs, right? Now we have to complete the cycle. So oxaloacetate should go back inside in the cytoplasm, but oxaloacetate cannot cross in a mitochondrial membrane. So oxaloacetate will be converted to aspartate. How? How oxaloacetate converted to aspartate? Do you remember I told you? Keep on adding amino group, oxaloacetate to aspartate to asparagine, they are formed, right? So here you add one amino group, aspartate is formed. Aspartate can cross in a mitochondrial membrane, reaches cytoplasm. Here amino group will be lost again and oxaloacetate is formed, right? So what is occurring here is that all the intermediates are revolving like this, but what change is basically occurring is that NADH is taken from cytoplasm and NADH is delivered in mitochondria, right? In this shuttle, as malate and aspartate are crossing in a mitochondrial membrane, so this shuttle is also known as malate aspartate shuttle, right? Now see the other shuttle, glycerol phosphate shuttle. In glycerol phosphate shuttle, in cytoplasm, DHAP forms glycerol 3-phosphate. DHAP is dihydroxyacetone phosphate that will form glycerol 3-phosphate. Name of enzyme is cytoplasmic glycerol 3-phosphate dehydrogenase, right? And here NADH is used. Every time in shuttle in cytoplasm, NADH will be used, obviously. We have to take this NADH in mitochondria, right? Now, glycerol 3-phosphate can cross in a mitochondrial membrane, reaches mitochondria. In mitochondria, glycerol 3-phosphate will again form DHAP, which can cross in a mitochondrial membrane, again reaches cytoplasm. So the cycle is complete, right? But what is the enzyme here in mitochondria? Now this is mitochondrial glycerol 3-phosphate dehydrogenase enzyme. And for this dehydrogenase, FAD comes to take hydrogen and forms FADH2, which can give 1.5 ATP in via ETC. So all these things are evolving like this, but what change is occurring is that NADH is taken from cytoplasm and FADH2 is delivered in mitochondria, right? Now this shuttle, glycerol phosphate shuttle, is more important in skeletal muscle and brain. Why? Why less ATP forming shuttle is given to brain? You can see one difference between the two shuttles, that this glycerol phosphate shuttle is a shorter shuttle requiring less intermediates, less enzymes, so very quickly it will occur. So it is a quick source of ATP. It is shorter shuttle, therefore it is quick source of ATP. Although less ATP, but it is a quick source of ATP. Brain has to act quickly, that's why this shuttle. Skeletal muscles are used in emergency purposes, right? So that's why this less ATP forming shuttle, but a quick source of ATP shuttle is given to skeletal muscle and brain, right? This is it with shuttles.